Greetings to everyone. Today, let's dive into something crucial in high school geometry, the geometry proofs. These are the problems that start appearing in high school and might have phrases like prove this or prove that. Let's explore this with an example. Imagine you're given this problem given that angle 1 is congruent to angle 3. Prove that line L is parallel to line M. You might look at the figure and think, these lines look parallel, but that isn't enough. You just can say, well, line L looks parallel to line M, so they must be parallel. And that's a no. You need to have a concrete justification or a proof. Proofs in mathematics are like arguments made by lawyers in court. A lawyer might say, this fact plus this fact, therefore this conclusion, convincing the jury. In geometry, we're doing something similar. We're just justifying our conclusion with logical steps. And the tool we use for this in high school geometry is the deductive reasoning. Now, when we talk about proofs at the high school level, we often use something called two-column proof. Let me explain how this works. Imagine a table with two columns. On the left, you write a statement, and on the right, you provide a reason for that statement. Statement. Angle 1 is congruent to angle 3. Reason. Given information. You continue this process by making a series of logical statements backed with reasons until you reach your final conclusion, proving what you set out to prove. Here's something important. The reasons you must based on solid logical ground. You just can say these two angles look equal. Your reason must come from of the following. First, given information. Information provided in the problem like angle 1 is congruent to angle 3. The second is the definition. Precise definition of geometric concepts. These are just examples. As you get more familiar with proofs, you see how these reasons come into play. Triangle, congruence, side angle side postulate. As with any proof, we always have a diagram, some given information, and some we need to prove. We can prove things by applying what we already know about geometry to a given information and the diagram as we construct a logical argument using a statement and a reason table. In this example, we want to prove that triangle GFK is congruent to triangle HFJ. In other words, we need to show that the purple triangle is the same size as the pink triangle and they are congruent. We start with a given. Line JJ and line HK bisect each other at point F. The reason is that it's given. To visualize, we know that JJ and KH bisect each other at point F, cutting each other into two equal halves. From this, we can conclude that segment GF is congruent to GF, and the segment KF is congruent to HF. The reason? That's the definition of the bisect. Next, notice we have a pair of vertical angles, angle GFK and angle HFJ. We can say they are congruent because all vertical angles are congruent. At this point, we should check if we have enough information to prove that triangle GFK is congruent to triangle HFJ. The answer is yes. We have two congruent sides and one congruent angle between them. So we can use the side angle side postulate to prove the congruence. Proof complete. I bet you're feeling a little better now after that first one. But let's move on to a more challenging one. triangle congruence, side postulate. Welcome to geometry proof. In this proof, we have a diagram, two pieces of given information, and what we need to prove that two triangles are congruent. Let's identify those triangles. We want to prove that triangle RSB is congruent to triangle RUB. Notice that these triangles combine to form a larger right triangle. Using the same strategy as before, let's start with the givens. Our first given is that R is the midpoint of the segment SU. Visualizing segment SU with point R as the midpoint, we know that midpoint cuts the segment in half. So, SR and UR are congruent. The reason? It's the definition of the midpoint. Our second given says that segment SB is congruent to segment UB, meaning they have the same length. Notice that both triangles share side BR since BR is a part of both triangles. It has to be congruent to itself. The reason? The reflexive property. We now have enough information to prove that triangle RSB is congruent to triangle RUB by using the side postulate. As each triangle has three pairs of corresponding congruent sides, proof complete. Line segment congruence. Angle side postulate. This proof is a bit more challenging. We have a diagram, some given information, and we need to prove that two line segments are congruent, not just two triangles. So, there's an extra step here. In this case, we want to prove that segment AA is congruent to segment DE. Our first given is that angle A and angle D are congruent. The second given tells us that angle 2 and angle 3 are congruent. Now, notice that triangle BCE has two congruent based angle, angle 2 and angle 3. We know that triangle BCE is isosceles by the base angle theorem. Since triangle BCE is isosceles, the side opposite of the congruent angles are also congruent. We can conclude that BE is congruent to CE because the definition of an isosceles triangle. Next, observe that triangles BAE and CDE have pairs of vertical angles, angle 5 and angle 6, which are congruent because all vertical angles are congruent. We now have enough information to prove that triangle BAA is congruent to CDE by the angle side postulate. Since segment AE and DE are part of those triangles, showing that the triangles are congruent allows us to finish our proof and conclude that AE is congruent to DE. Introduction of absolute value. The absolute value of a number, denoted as the value of x, can be understood through two primary definitions, a geometrical definition and an algebraic definition. In this session, we've delved into geometrical perspective. Number line. As we know, all real numbers can be represented on a straight line known as the number line of real numbers. In the middle of this line, we place the number 0, which refer to as the origin. To the right of the origin, we have positive direction containing the positive numbers, while to the left, we have negative direction containing negative numbers. You can see this clearly in the diagram in front of us. Geometrical definition. With the number line in mind, we can now define the absolute value of number x as the distance between this number and the origin. It's important to note that since distance is always positive and the positive value is defined as distance, The absolute value of any number will always be greater than or equal to 0. Example 1. Find the absolute value of 3. According to the definition, the absolute value of 3 is the distance between 3 and 0 on the number line. This distance equals 3 units, so the absolute value of 3 is 3. Example number 2. Find the absolute value of negative 5. Now, let's calculate the absolute value of negative 5, which represents the distance between negative 5 and 0 on the number line. As shown in the diagram, the distance is also 5 units, so the absolute value of negative 5 is 5.